Welcome to module 29 of database management systems. We have been talking about indexing and hashing, and this is the fourth in the series. In the previous three, we have talked about different aspects of indexing, and specifically in the last module, we have introduced the most powerful data structure B plus tree for index files. In this module, we will take a look into explore into various hashing schemes for achieving the similar targets. We will look at static and dynamic hashing, and we will then compare it between the ordered indexing that we have discussed already and hashing, and we will also understand about what are called bitmap indices. So, these are the module outline. So, static hashing, I am assuming that all of you know about basic concept of hashing. So, what it does, there is a bucket is a unit of storage containing one or more records. So, that is the basic logical concept. Typically, in physical terms, a bucket can be a disk block. So, a hash file organization obtains, in a hash file organization, we attempt to obtain a bucket for a record directly from its search key value using a hash function. So, this is where it becomes very different compared to the ordered indexing for which we saw all this ISAM method and the B plus tree, where we went through different index structure, but here we want to make use of a mathematical hash function. So, that given the key, ideally I should be able to get the bucket in which that particular record containing the key exists. That is the requirement. So, hash function H is a function from the set of all search key values k to the set of all bucket addresses b. So, it is a mathematical function, and it is used to locate the records for access, insert as well as delete. Records with different search key values may be mapped to the same bucket, right. This is not what ideally we wanted, but it is possible. Thus, the entire bucket has to be searched sequentially once you reach there to locate a record. We can make use of other techniques there, we will come to that. So, let us take a quick example, hash file organization of an instructor file using say department name as key. So, we need to design a hash function. So, let us assume that on the address space B, we have 10 buckets. So, every bucket is designated by a serial number, bucket 0 to bucket 9, and we take department name is a key. So, it is a character string. So, we take the binary representation of the ith character and assume it to be the integer I. Simply every character you take its binary representation and think as if it is an integer, and then as a hash function we add these integer values of binary representations modulo 10. So, m hash value of music, we take the binary representation of m, which is the ASCII code of m, capital M, then add the ASCII code of u, the lowercase u, and so on, and do that modulo 10, and we get a value which is 1. So, naturally, since we are doing modulo 10, which is the number of buckets here, so we will get a result for the hash function which is between 0 to 9, which is the bucket address where it is expected. So, here we are showing an example. So, you can see in the earlier slide we are showing music is 1, history is 2, physics and electrical engineering both have hash value 3. So, you can see here in bucket 2, since history has value 2. So, those records LSED and Calipari records go to bucket 2, whereas physics and electrical engineering both have hash value 3. So, that Einstein, Gold and Kim all go to the bucket 3. Similarly, it happens with the other buckets as well. Not all buckets are shown here, only 8 buckets are shown, but in this way we can actually directly map them to the buckets. And so, such a hash function would be really useful. Now, the question is it is a mathematical function. So, how good or how bad it is? So, we will say that the worst possible hash function is one which maps all key values to the same bucket. So, that everything will have to be then done serially. So, that is of no use. So, the ideal one would be which will distribute the different search keys values in different buckets in an uniform manner to from the set of all possible values. So, that will be nice to have, and ideal would be that if the hash function is random, which means that so that each bucket will it will generate from the key value, it will generate the bucket number, it will generate the bucket address in kind of a random manner, so that in a random phenomena, so that irrespective of what kind of actual distribution the search keys may have, the buckets over which they distribute will be more or less the same. So, every bucket will have same number of records, things will be balanced. A typical hash function performs computation on the internal binary representation of the search key, that is the basic that is the one that you have just seen. So, if it is a string, then you treat the characters as their binary representations as integer, do some sum modulo a number, exactly what we did in the last case. Now, the question is the buckets have a certain size. We said that a bucket is a disk block. So, a bucket can overflow because there may not be enough sufficient buckets to keep all the records. So, it will not fit in, or your distribution could be skewed. So, there may be many buckets where there are a lot of space left, but some buckets may have too many records coming onto it because of the behavior of the hash function. So, that multiple records have the same key value, or chosen hash function produces non-uniform distribution and so on. So, if that happens, then the probability of bucket overflow will happen, and we can try to reduce that, but it cannot be eliminated. So, all that you do is to have overflow bucket, which is nothing but having other buckets connected to this target bucket in a chain. So, this is called the overflow chaining. As you can see, there are 4 buckets shown here, and bucket 1 we are showing are connected with other 2 buckets, which are the overflow buckets for bucket 1. So, this kind of a scheme is called close hashing. There is an alternate scheme called open hashing, which does not use bucket overflow, but it is not therefore suitable for database applications, and we will not discuss it here. So, hash indices can be used only for file organization. Not only for file organization, but they can also be used for index structure creation, like we did for B plus tree. We can use the hash indices for index structure also. So, a hash index organizes the search keys with their associated record pointers into a hash file structure, exactly in the same way it is hashing otherwise. So, but you can note that the hash indices are always kind of secondary indices, because if a file itself is organized using hashing, then a separate primary hash index on it using the same search key is unnecessary, because if you are talking about primary hash indexing, then it will mean that you are taking the primary search key and creating a hash index on that, but if the file is created by hash indexing, then that already exists. So, anything that you create in terms of indexing is basically a secondary indexing structure in a hash organized file. So, this is a kind of a hash indexing example. So, here I am showing the hash indexing with the ID of this table, and the index is computed by adding the digits modulo 8, assuming that there are 8 buckets. So, if you take if you look at bucket 0, then the key that has gone there is 76766, which is 7 plus 6 13, 20 plus 6 26 plus 6 32 modulo 8 is 0. So, it goes into bucket 0, it happens that way. But if you look into bucket 4, you will find that the 4 IDs actually all have this value 5 under the hash function. So, they all need to go to this bucket, and therefore, but the bucket size assumed here is just 2. So, after the 2 indices have gone in there, a overflow chain is created and another overflow bucket is used to keep the next 2 IDs there. So, this is how a hash index can be created. Now, this is this kind of a scheme where you start with a fixed number of buckets, and then you design a hashing function which maps the search key values to this fixed set of buckets, is known as a static hashing. It is static because you start with a fixed number of buckets. So, naturally the question is what should be this value of B, the number of buckets. Now, if it is initially too small, then the file keeps on growing, the performance will degrade, because you will have too many overflow chains, and all advantages of having done the hashing will get lost. On the other hand, if you take a too large a B, then you will unnecessarily allocate a lot of space anticipating growth, but it may take a very significant amount of time to utilize that space. Or also it is possible that the database at a certain point of time grew to a large size, and then it started shrinking, and then again space will get wasted. So, static hashing has these limitations. So, naturally what you will have to do is to periodically reorganize the file with a new hash function, which is certainly very expensive, because it changes the positions of all records. So, it disrupts the normal operation. So, it would be better if we could allow to change the number of buckets to be changed dynamically as the database grows. So, if the database grows, it can use more and more buckets, and if we could adjust this in the hashing scheme inherently, then it will certainly be better as a solution. So, that gives rise to what is known as dynamic hashing. So, it is certainly good for databases that regularly grows and shrinks in size, allows the hash function to be modified dynamically. Of the different dynamic hashing schemes, I will discuss the extendable hashing, which is a very popular scheme. So, let us see how it works. So, the hash function will generate a value over a large range, say typically a b-bit integer, say 32-bit integer. Now, so what you have is you have generated a value which is a hash value, which is say over 32 bits. But what you do at any time, you use only a prefix of that, you only use a frontal part of that to index the table to the bucket address, and the length of that prefix is I bits. Now, naturally it could be, at least theoretically, it could be 0, that is, you do not use any prefix, and it could be up to that you use all the prefixes. And so, therefore, if you are using I bits, then the bucket address table, the possible bucket addresses that you could have is 2 to the power I. Initially, you keep that as 0. So, then the address table will actually point to different buckets. Let us start moving to an example and see what is happening. So, this is the general scheme. So, you have a hash prefix which is using I number of bits, and for different values of I number of bits. So, there will be 2 to the power I entries naturally. You have different buckets here, but you may not actually have all 2 to the power I buckets. You may have less than that, as it is shown here that bucket 2 and bucket 3 exist, but bucket 1 is a holder for both the prefix 00 as well as prefix 01. So, and on top of every bucket, you have a kind of bucket depth given. So, it is the number of bits that you need to explore in the representation so that you can distinguish the different records of that bucket. Naturally, the maximum value of any of these I is the I here, but it could be less than that. So, I am sure this probably is not making much sense immediately. So, let me move to a detailed discussion. So, what I was saying that each bucket j stores a value I j. So, this is all the entries that point to this bucket has the same value on the first I j bits. So, this I j bits are identical. So, all of them have come to this bucket. So, how do you locate the bucket that contains the search key k j? So, you compute the hash function, which is x, use the prefix I bits of x as a displacement into the bucket address table, and follow the pointer to that appropriate bucket. Now, if you have to insert a record with a search key k j, you will follow that same procedure as the lookup, and look at the bucket j, and then you will have to look for making some space. So, let me do something, let me before going through this statement of the algorithm, let me just go through an example first and we can come back to this formal statement. So, what we are trying to do is there is the department names which we are using as a key to do this hashing index, and they are represented in terms of the binary representation. So, this is the hash of that department name, and hashed into you can easily see this is 1, 2, 3, 4, 5, 6, 7, 8. So, this is hashed into 32-bit number. Now, what do we do? So, initially we start with, so this is all the different hash values that you can see. I am sorry, this is all the different hash values, and this is the table that I need to actually represent. Okay. So, initially there is nothing. So, I try to I will try to insert Mozart, Srinivasan and Wu, these 3 records here. So, let me try that. So, if I look at Mozart, then Mozart is from the department of music. So, and Srinivasan is from computer science, Wu is from finance. So, let us look at this. So, Mozart is from music, Srinivasan is from computer science, and Wu is from finance. So, these are the 3. Now, if you look into the prefixes of their hash values, you can see that their hash values are 1, 1, and for music it is 0. Right. So, if I use a hash prefix which has just 1 bit, and naturally therefore, I have 2 entries 0 and 1, then music with the value 0 maps to this bucket where I entered the record for music, and computer science and finance, the records corresponding to them has a hash value prefix 1. So, they both map to this record. This is how it can get started. So, you find out while inserting, you find out where it is Mozart, and based on that you create this. Now, let us try to insert Einstein. So, to insert Einstein, what do we find? So, what all we already have? We have music, we have computer science, we have finance, and now Einstein comes in. Einstein is from physics. So, what would happen when you try to insert Einstein? You already had computer science with 1 as 1 prefix and finance with 1 prefix. So, you had in bucket 2 corresponding to 1, you already have 2 records. That bucket is full, assuming that it can take only 2 records. So, now you get another which is value 1. So, its value is 1. So, what I need to do? I need to actually expand this. Now, how do I do that? I cannot expand this because there is no more space left. So, all that I need to do is to actually expand the bucket address table. So, earlier if I just go back. So, if I just go back, earlier we had only 2 entries because we are using only 1 bit in the prefix, and with that I could not have inserted Einstein, who is from department of physics, which also has a 1 bit prefix which is 1. It was so. I need more space. So, I have increased the prefix level to 2 going here, and now naturally I have, if I have increased this to 2, now I have let me erase this these entries, and now I look at for music I look at 2, for physics 1 0, for finance 1 0, for computer science 1 1. So, now I find that after I have moved from looking at one bit of prefix to 2 bits of prefix, now finance and computer science, which was earlier together because I was looking at one bit, now becomes different, but finance and physics both come to the same 1 0. So, in the hash bucket address table 1 0, you have finance and physics coming in with Wu and Einstein records, and computer science, which has got 1 1, the Srinivasan record goes to a new bucket which comes from 1 1 here. Now, the interesting fact is what happens to Mozart, who was there. If you remember the earlier structure, this is, we had only 1 here. So, this was going to Mozart, this was 1 and Mozart was here because music had a prefix 0. Now, music has a prefix 0 0. So, what you would have expected? You would have expected that therefore, since the 0 0 has come in, 0 1 has also come in. So, you would have expected that to have another bucket here which 0 1 is. But then you observe that actually that would be quite wasteful to do, because you do not actually have a record which has a prefix 0 1. Out of these two, which are, we are looking at 2 prefixes, but you do not really right now need to look at both the prefixes. You can still resolve just by based on the first prefix 1. So, you do a simple trick, you do not change the prefix level of the particular bucket, you say it is 1, because it is, you just need to look at 1 bit to be able to come to the records in this bucket, and the globally it has changed to 2 bits prefix, but locally you keep it as 1. And with that what you have? You have 0 1 which has a bucket address table entry, actually does not have a bucket because there is no records for that. So, you let that point to the same bucket. So, this is a very critical observation, that these numbers are basically the local depth, the local information of how many bits in the prefix you need to look at to be able to resolve for coming to this bucket for the records that you currently have, whereas this is the global one, this is the global maximum that you have. So, naturally local depth cannot exceed the global depth, but if it is equal, then you have a unique mapping from the bucket address table entry to the bucket. But if the local depth, as in here, is less than the global depth in terms of the number of prefix bits you are looking at, then multiple bucket address table pointers actually end up in the same bucket, and that is the main principle of this algorithm. We can just continue further inserting gold and said into this. So, as you try to insert gold and said, gold is also from physics, which you already had. So, physics and said is from history, which we did not have. So, you have history, finance, computers. Let me just mark them by the side. So, you have now computer science, finance, history, music and physics. Now, you will find that you need to you now have physics is 1 0 and you have 2 records for that, and music is continues to be 0 0 obviously. History is 1 1, same as computer science. So, that has to go on this, and finance is on 1 0. Now, but what happens is, when you try to do this, you could not have inserted more records because you have run out of space in the buckets. So, again you have run out of that. So, you need to expand in terms of the number of bits that you look at. So, you increase that to 3 and now you have 0 0 0 to 1 1 1, but as I have explained, not all buckets really need to look into so many bits. Mozart, this bucket continues to be with a local depth of 1, because if you look into all these 4 different cases, then music is the only one which has a prefix 0, everyone else has a prefix 1. So, if I know that it is 0, then it comes to only this bucket and nowhere else. Consequently, all these 4 bucket address pointers actually go to this bucket table, whereas these 2, for physics I have 1 0, and for finance we have 1 0 here, and these come to. So, physics now is looking into 3. So, it is 1 0 0, finance is into 3, it is 1 0 1. So, both physics and finance go to different buckets. Now, coming to computer science, it is 1 1 1, and there is no. So, computer science is 1 1 1, and there is no 1 1 0. So, the 1 1 0 bucket address table pointer continues to point to the same bucket, and the local depth value is just 2 less than 3 in the global table. So, this is the basic process of doing dynamic hashing. So, I will not. So, the whole example in terms of this table I have given here worked out. So, you can just go through every step and try to convince yourself. This is an interesting case that happens here, where again you come to computer science professors to be entered. So, at level 3 of prefix, you have all of them have prefix 1 1 1. So, you would have required to split or increase the prefix level, globally the prefix level to 4. But assuming that there is an upper bound on the number of prefix levels you can do, which decides the size of the bucket address table, if that is given to be 3, you certainly cannot increase it further. So, all that you will have to do is actually do a kind of an overflow chain here as well. So, all of them are 1 1 1 here, which brings you to this, you cannot find it, you go to this, and all 1 1 1s in future will have to be. So, it is kind of a trade off between what is the size of the global depth, how many prefixes globally you would like to look at, what is the size of every bucket that you will have to maintain, and what is the kind of chaining that you will have to accept because of that. So, this is what happens particularly. So, you can continue in this way, and this is a final table where all things have been hashed well. So, this is the basic extendable hashing scheme. It has in this, the performance does not degrade with the growth of the file, and there is very minimal overhead of the space, but it does have disadvantages. For example, there is an extra level of indirection to find the desired record, because it is a hash, then come to the hash bucket address table and then go to the bucket. Bucket address table itself may be very big, because it is exponential in the size of the number of bits. So, it could be larger than memory, if that so much of contiguous allocation may not be possible. So, you will need to have another possibly a B plus tree structure to locate the desired record in the bucket address table first, and then changing the bucket address table will become quite an expensive operation. So, the growth will become. So, there are several disadvantages that also this scheme has. So, another alternate is to use a linear hashing, where it allows incremental growth of its directory at the cost of more bucket overflows, of course. Now, I would quickly try to compare the two major schemes that we have discussed, the ordered indexing and the hashing. Now, naturally, ordered indexing suffers from the cost of periodic reorganization, and because the indexing will have to be maintained. The hashing is better in terms of that. Relative, you will have to look at the relative frequency of insertion deletion, that decides much of the cost going between these two schemes. You will have to see, is it desirable to optimize average access time at the expense of worst case access time. For example, there could be several ways to organize, so that your average your worst case may be really bad, but as long as your average is very good, you should be happy about it. So, those kind of hashing schemes should be more preferred. So, you also depends on the kind of expected type of query. So, for example, hashing is better in terms of retrieving records which have a specific value of the key, because you can directly map from that key to the bucket. And if range queries are common, then as we have seen, ordered indices would make much better sense, because in terms of the ordering you can quickly get all the required records at the same physical location, nearby physical location. If you would like to understand as to what the industry practices are, it is very mixed, and if you just look into 3 of the very common database systems, PostgreSQL does support hash index, but does not recommend it because of the poor performance. Oracle supports static hash organization, but not hash indices. SQL Server supports only B plus trees, no hash index based scheme. So, of course, you can see that there is the community is mixed in terms of its reaction to whether it is indexing or hashing, but hashing powerful, at least in limited ways, is a powerful technique to go with. The last that I would like to just quickly take you through is what is known as bitmap indexes. Bitmap indexing is a very simple idea. So, it is a special type of indexing which is designed for querying on multiple keys. The basic idea is that if let us assume that all records in a relation are numbered from 0 to n, and let us say that you are talking about attributes which can take very small number of distinct values. So, bitmap indexing is not for any attribute. So, consider attributes which have very small number of distinct values, say gender, which has 2 possible values or few possible values, the country, state. So, take those, or maybe you can nominally bucket a range of numbers also, income level 5, 6, 10 income levels. So, small range of possibilities. And bitmap is simply an array of bits. So, take an array of possible array for the records, and for the possible values you mark 1 or 0. So, here is an example showing it. So, we are showing bitmap index for gender. So, you have a array for M, the male gender, and F, female gender, and if you look into the record 0, 76766 has male gender M, and therefore, in the male gender bitmap index, the first bit is 1, in F it is 0. So, actually M and F are complementary. Similarly, for the income levels, you have 5 different bitmaps encoding the 5 different possible levels in the income that you can have. Now, the big advantage of bitmap indices are doing different queries on multiple attributes, and for example, often queries have intersection union, and they can be simply computed in terms of bitmap operation. So, if you have 2 different values to conditions to check in terms of bitmap indices, then you can just make their and whatever satisfies. So, say if you are looking at males at for example, here males at income level L1, then you can just take the bitmap for gender and the bitmap for income level and do the ANDing, and you get that the first record has value 1. So, that is the answer, and you can quickly come to that. So, bitmap indices are generally very, naturally they are small in compared to the relation size, because you are doing bitmap indexing only if the attribute can take small number of distinct values. Of course, the deletion has to be handled properly. Look at this, and should keep bitmap for all values. Even if there are null values, you must keep that, otherwise you will lose track of that. And there are several efficient implementations. Some information I have given, but we do not want to go in much depth here, but several compression techniques are possible in terms of bitmaps. In the next module, I will talk a little bit more about how to use that. In this module, to summarize, we have talked about various hashing schemes, static and dynamic hashing, compared the ordered indexing with hashing and introduced the notion of bitmap indices.